Hello, hello. So, um, the last time we have implemented our own uh, very fundamental um, CX list class. So, a class that can be used to represent lists in general. And the way it works, it also allows us an access by index, so it can also be used for arrays, although it does not provide a continuous memory uh, layout, so that we can not just get the first element and then by adding pointers using pointer arithmetics then just get the address of the next element. We always need to use the add function to obtain the next address. This works, this is the general description. If we are using elements stored in our list which are smaller or equals to the size of a pointer, then we are just reusing the internal array to store the data directly, in which case we would have a consecutive memory block. But since this is not guaranteed for all the sizes, and also depending on the architecture for which you are compiling, the pointer size may vary. So uh, the use here is very much an internal implementation artifact, meaning that you cannot rely on the memory being consecutive usually, and you should not. You should always only rely on the documented features of your classes, because if they are documented, then they are expected to be maintained. If they are undocumented artifacts, then they may be changed at any point in time, which would then break your own code. And since I think generally being able to create own container types is a quite useful thing, today we will simply take a look into creating yet another own container type. In this case, a CX map, so a object that stores values not by index but using a key and the value pair, so that for any given key you can retrieve the value that has been stored under it. And we will also think of some homework for you to do. Some homework will be related to the CX list, since you already had time to get familiar with it, and depending how far we go implementing the CX map, there will be some homework with it, or we might need to finish the implementation during the next lecture. Also, it's important to note that during the next lecture, that will be well the last lecture before the holiday break. So it would be good if you have any questions you want to ask, if you would use the opportunity next week to ask everything you ever wanted, but never dared to ask before, so that you have as much information as possible going into the holidays. Um, or if you just want to enjoy the holidays, then maybe it's not what you want. But well, that's up to you. My strategy was always to use the holidays to be even more productive than usual. So we will here obviously start by creating a new header file for our map. You can provide the name xmap. Now, likewise with the CX list, where we kind of said we are creating a list but gave it features of a vector, kind of a bit like Qt does it, by the way. Here with our xmap, we'll also um, kind of make it a bit more, not exactly what would be a map in STL. So in STL, a map would be a binary tree. So the internal data structure would be a binary tree, but such trees are quite difficult to maintain. Well, difficult. They just need much more code to make them work and properly and be always balanced. A much easier, much simpler approach is to use a hash map, which often even has advantages, but also is a bit more picky. So a hash map can, in certain scenarios, be worse than or rather, it's called a hash table. But you know, a table map, these terms can be used interchangeably. But the most common term in the literature is a hash table. So our map will technically inside be a hash table, and also on a note on this, in other languages, like for example C sharp, which is kind of a modern, how to say it, a modern take of what C++ could be if one would want to be it to be modern, or in this case they wanted it to be modern. there you don't have maps in that sense. You call your container types that have a key and a value as dictionaries, and usually they use internally also hash tables. Although the way they are implemented, it's not like that you can rely on any particular use to always work in a given way. Usually it's simply made such that you have the specified interface, and internally it might be implemented as a hash table or it might be implemented as a tree. It might be implemented as both, and the system will use whatever appears to be more efficient and at any given moment. So there's quite a lot of flexibility in the implementation of the backend, which is hidden from the user. In our case, since we're implementing in for our own use, we will be very conservative with the amount of code we want to write. So we will not make like multiple parallel implementations. Instead, we'll really concentrate on implementing one particular efficient way of doing things, so that we also can rely on the mechanism always behaving the same way within its specification. So CXMap, as you see, just copied a piece of our list code. I might actually copy even a bit more. We definitely will need a release function. We'll need some create function, expand, not in this way, expand will be quite different. Yes, and it's protected, so we don't want to expose this implementation artifacts. Create, I could maybe even leave for now. Let's just comment out whatever we don't need yet. Here we just want this to be so that it compiles, and of course our CXMap will have two template values, type and value, and of course this will also need to be changed. So in a hash map, the way this works is in a hash table, the way the data are stored is you have a table which basically is an array of buckets. A bucket is a list of entries, and in this array of buckets you can select individual buckets by a hash value. A hash value is calculated from the provided key. So we will want first of all to define a data structure that will represent such a bucket, or rather an entry in a bucket. So struct as entry. Let's see what we need. We will definitely want to hash the to have the hash value. So usually it will be a an unsigned int 32-bit. So we just use unsigned int. We could use unsigned long to be on the safe side. That will be the, always 32-bit in any architecture, but usually, of course, on any modern CPU, int will be at least 32-bit, so that should be fine. So we call it hash. Then what we'll need is so we need to decide how we want our buckets to be structured. We could of course go all out and use a XList, for example, for this application, but that kind of would add a unnecessary dependency. So here, also for the reason of demonstrating the different type of implementing a list, what we'll be using will be a singly linked list. So the first element will simply have a pointer on the next element, which will have a pointer on the next element, and the next, and so on. So here, the way this works is that we will be able to traverse the whole list in one direction at any point in time, and keeping the right pointers, will be able to easily remove elements. And whenever we add elements, this we will have to decide. We will either want to add them at the very bottom, which would need us to keep one more pointer, or we will do the simplest thing and just add them at the top, which works without keeping an additional tail pointer. And for our application, this will be good enough. It usually also is a bit of a expected behavior that the last element of a given type which you enter is the first one then to retrieve. We can later also think about modifying our map to be able to be a multi-map, so that we can store multiple values under the same key. For example, Qt, if I remember correctly, did it such that they really have just one map implementation from which they just derived either a multi-map which can have multiple values, or just a map with a single value. And really the only point where this plays a role is the insert function. So we could actually go here a different route. Instead of defining different types, we could just have a argument for our insert function which will specify whether we can insert um, and maintain an already existing element for, or rather all the existing elements for a key. So if we insert without the parameter, I think this will be the most elegant approach for us. Then we remove all entries with the same key and only insert the new one. And if we set the parameter insert multi to true, then we will insert and leave whatever is there be. Also, such multi-insert would technically be faster, since whenever we are inserting something into a bucket and we would not want to have key duplicates, we need to check in the bucket if there are entries with that key. If we don't care for that, we just insert the new value at the top and don't even need to iterate through the entire bucket. So we have our next entry. Then we will want to store the key. So v key, and we want to store the type 10 type. So we will have two elements here already always stored. In this case, we are relying on the built-in mechanisms for copying and assigning values. So we could, of course, go with a more low-level approach as we had with list, where we just have pointers and then have manually call new and destruct and so on them. But usually for a map use case, you are more concerned about the whole thing working reasonably fast with a lot of entries than the single operation be fast. The reason simply is that such data structures are expected to scale very favorably with a high amount of elements, so you don't need to compare all of the keys, etc., like you would have if you just go through a whole list, but instead through a, let's say, smart use of mechanisms, the whole thing works very efficiently, even though a single operation might not be super fast. We could, of course, later look if we can improve the performance by using some more low-level approaches with regard to the key and value storage. But for now, I think this is good enough. Right. I think this code for now we'll just remove. I think it's more pedagogical if we just write everything from scratch and not copy code around. This helps to make things fast, but usually is not as descriptive. So obviously what we need now will be some additional variables, although I would say that we will at least keep the initial map thingy, simply because if we later want to extend our object with a copy and write mechanism, it will be expedient for us to have all the data already on a internal object, that we'll need to adapt this object, not just rename it, of course, but we'll also need to change everything that it contains. So first of all, we will want so a size we can keep, because we always want to know how many elements are without having to iterate through all of them. This is a very convenient variable to have, especially if you want to check if something is empty. Then a capacity we will also need, and then as a third value we will have what we want is an array of pointers to our entry. So we will call it p buckets. And this one, and the capacity will refer to the amount of buckets we have. We could also call this a bucket count. This is better. Let's call it this way. Bucket count. We could then call like bucket array, but let's just stick with buckets. And then of course we will need here to adapt our create, where we can create a new count. Right, and since we want to be efficient, we can a array like this. So an array of pointers with the size null. So then we can here we need the size of xmap plus the size of entry asterisk times new count. Size is 0 of course, and new bucket count is count. And what we also need is we need to initialize our buckets all with null. So memset a new oops, new buckets comma 0 comma we cannot use size of we just use this here that gives us the right size. So all the buckets are null, so they are not pointing to anything, and generally the way the hash table works is that not all buckets may contain an entry. Ideally, this is our goal. We would want for top performance to have every bucket containing exactly one entry. But this, how well this will work, often depends on the quality of our hash function. So this will require us to so generally what we want is of course to pick a good hash function, but we might also want to have a mechanism that optimizes the table for a use with a non-optimal hash function, so that for example you would have usually only half as much buckets as you have entries. So we can limit our grow function to save some memory, especially if we know that given special hash functions we might end up with a lot of hash collisions, i.e. different input values resulting in different in the same hash value. So in this case multiple entries with the same hash end up in the same bucket, but they have a different key, so we need to then search in that bucket for the right key if we want to retrieve the correct value. Okay, so these will be our most basic internal parts, and what then we will of course need is our insert function. So we can give it a return value. There are, for example, map implementations which do not allow you insert if there already is a value with that keys. So we could have a second argument here that would tell us if we are allowed to insert or to override something, and then we would want a Boolean parameter such that we can return false if the element already existed and was not entered. I think that might be useful, so let's go with that. Bool insert, and the insert of course takes a key const right, and this should be k and v for key and value. Right, const k reference key const v value, and then insert multi, and the other one will be no replace. I mean, we could also introduce an enum which specifies the mode, which might even be more elegant. Plus, you learn using enums. Insert mode, and we have let's how do we call it? One would be just normal, and no replace. So normal is 0. The other ones get auto incremented to 1 and 2. So instead of using two arguments and have a situation where we might have inconsistent arguments, we just have one argument which takes the mode, and then from that we know what to do. So now we return false because we return an error. Also, in case we encounter some memory allocation issue, we could also return false even for type normal or type multi, but that usually would not be ideal, because if you don't expect return false only in case of a memory error, then it would be better to in this case throw an exception since the error probably would not have been handled anyways either. And then of course the next thing we'll need is a lookup function, so something that finds us an entry. And how we do that best is again up to some extent our preference. We could do it such that we need to provide a variable which will receive a copy. You could make it such that we'll always get a pointer to the internal element if there is any. We could also return by reference, but then we would need to throw an exception if we are asking for an element which does not exist. So normally you would want to have a certain symmetry between using between which argument types you pass to insert and what you get out. For example, the approach of Qt is that your get function always returns you a value, but if you want to get something that does not exist, then you just get a empty element constructed for you. But this also means that the return values are not by reference, which would be convenient, but are by type. So what I would suggest is we first implement a function that will give us an element if it exists as a pointer and null otherwise, and the other use cases and the other implementation, other functions we can then implement based on that. Whether we leave the function later here publicly available or move it to the protected section, we will decide later. So v asterisk get value pointer, or just get pointer, get value insert. We'll just call it get pointer because it's obviously it's a value, and this only takes a key. Again, since we are not yet ready, return null. We will need to implement that, and of course we will want to start with inserting. So well, let's start with implementing the insert function. So first thing we will need to do will be to check if we if we need to create a new M object. Although we could probably move this into our resize function directly. So maybe we will start first with just creating a new entry, because this we will definitely need. So entry is like new as entry. As you see in this case, we will not be using as entry. We'll not be using malloc. This time we'll be using new. Since we want the constructors for key and value to be executed for us for these entries, and we could of course check if entry well is null, then return. But usually, if you are using new, we expect it to work, and if it fails due to memory allocation, it should throw an error of its own. So at this point, we also don't need to zero it. We can just specify initialization values here, and then the constructor will a constructor implemented for us by the compiler will just initialize those values. So this is quite convenient to use it this way. And then we can of course already start with assigning values. So entry key is key, entry value key, right, that should be key. Value is a value. The next remains at null. The hash will need to compute. Hash is equals right, and this is now the point where things get complicated, because we need a hash value, a hashing function. So for start, I will just add a function here which will take a value and sorry, a key, and then just hash its memory size. But this would of course not work for more advanced types, or we could do it more complex from the get-go and add a function pointer that can be specified when creating the map, which will then be used to calculate the hash values. So for example, with STL, if you look on some, we have strings, so if you look on the implementation of string, it has here, well, it's derived from basic string, we need to find that, but it takes here, so let's say default, a set of default template arguments, which can be used, for example, here an allocator, which will define what we use to allocate memory. This is quite convenient, so we could in a similar way implement a helper class, which we could use to hash things. And I think that probably would be a good approach for us as well. So it makes the thing much more complicated, but at the same time much more flexible. So class, call it hasher, and then here we will just hasher, or we just call it h. That sounds nice. So h hash, and then it takes the key as argument. Okay, so now what we will do is we will put a breakpoint here and quickly implement a test case so that we can hash some key. So let's add here our xmap, and at the very end here, so xmap, cxmap, map. So key will be, let's say, an integer, or let's go with char asterisk. That is of course a more problematic type, but why not? A value will be let's use our own string class again with char. Okay, but that's boring. So let's start with just int as key and then string as value, and our hasher will need a class for that. So send long hash cx string reference key, oops, public static unset, right? Return null, we will give it a body later. So here we just add our we need to copy the name as type name here, oops, right? And now if we sorry, we have int for now, so let's int hasher. And in case of int, we don't need to be too complex, we just call it int hasher. And since it's an int of already the right size, we can just return whatever we got. This is not ideal, so usually you would want the hash function to introduce some more randomness to your hash values to spread it better out over the key space. But for now, since we want this to be as simple as possible, let's do with this. So insert 1 and 1. That will be our approach. So if we put a breakpoint here, we should have end up here and have, of course, the key being the hash. Oops, the hash being 1 with an arrow. Right, double point. So we have hash 1 and key 1, and now if we would want to improve our hash function, we could what we usually do is simply have some starting value to which we XOR our key. So let's say we want to find a nice binary pattern, so let's go with binary 1010. hex, this is A, so let's take 0x AA, and then a few more A's, and this will be XORed with key, and this will be our hash value. This is still a terrible hash function, but at least it does something to look a bit like a hash. So for now it's fine, and later we will of course look into how to improve that. Right, so we have our hash function. We already have assigned data by copy. What probably would be a good idea is first to check the type, and then first to check if there is already something, so whether we want to return false, but we will add this later. Now we want to make the hash table work in the first place. So we have our hash, we have our entry. So now what we want to know is we want to find out into which bucket to put it, and of course we also want to find out if we have enough buckets. So in the simplest case, we just check if where's our function m. So first of all, if m does not exist, then we need to create something, or the other case. So m buckets, bucket count. So if bucket count is equals if bucket count, let's say, is less than size plus 1. So if we have less buckets, then we will have entries. Then we decide that we need to create something bigger. And of course we will not like increase it by 1, but we will increase it by some factor. For example, we could double the size of the hash table. So int new bucket count will be equals and now of course the question is, do we have a bucket count or not? So bucket count, let's say plus 1, that we always have a value that's non-zero, and then we multiply this by 2, and this is the new size we want to have for our table. So we'll now need to use the create command here, although we should probably rather use a resize command, since we want the same function to work also when we will change the table size. So let's create here a void resize table. It will take the new bucket count as an argument. We should also always use size t. I think I used int here, so this was not pretty. Zack. And we just invoke here our function. We could have a return value and return false on error, but I think for now we will just define it such that whenever there is an error, then we will throw an exception. So this should be fine enough. So here now we need to look into our table resize function. So the way this works, there are of course a couple use cases. So one is if there is no m at all, and the other one is of course if there already is some m. So first thing we can do is we can create the new element. So we can just create for that as xmap new m is equals create new bucket count. Right, so we have this. We ignore of course errors. It was already fully initialized. Memset. We still use here malloc. We could in principle go here to use a new. No, we could not, because we have different size. We need to stick to malloc, so we leave it as is. So we have created our new object. Now we will need to check that we created it with enough entries. Right. So now we need to check if an m already existed, and we also need a variable here which will be the first entry per per let's call it p head as the and to indicate it's the first entry in our list. So what we will want to do now, if there was an m, is we will iterate through all the buckets and collect all the entries and put them into this linked list here. So we'll be removing it from the entries from the old m and adding them here. And once we are done with that, we will dispose of the old m, so we'll call release here. And then in the next step we will re-add all the existing entries that we have saved before to our new bigger bucket list. Okay, so for size t I is equals null, no, we want to start from the back, so I is equals m bucket count I something like that. Okay, so s equals m equals m buckets bucket count. Right. So the way this works is we initialize this here with a value which is kind of the count, so a kind of one bigger than the last value. Then here we do first a check, so we already decrement it by 1. And then here we can use I directly, as it will be a valid index. So we do it for every bucket we have, and in every bucket, while entry is not null. So again, as entry per next, which equals entry next, then entry next is equals entries is like entry, and entry is equals next. Right. And this should ensure that we will collect everything. An issue that is apparent here, if one would think about implementing some copy on write mechanism, is of course that our entries themselves are not immutable, so we will be modifying them. So if we would want to really properly do a copy on write, then we would need here to recreate all the entries and not modify the existing ones. But that's a problem for the later us, so we might not do it just at the end. We might just keep it as a deep copy sort of class. So this will be to be decided later. Right, so we have our m, we have released m, then now we could make m is equals new m. Actually it does not benefit us to have pre-created. The only benefit would be that we could fail and then throw an exception without having things here in a inconsistent state, although that probably is even not so bad. So let's stick with this design. And now we just need to add everything back to where we started, so we can copy something from here. So basically kind of we have one huge bucket called head, and now we will just distributing the entries where they should be. So we again need a next, since the previous next will be invalidated, and we will need entry next. And here we will add the use of another helper function insert entry, which will just take the new entry to be inserted. And it will just insert it into the at the right position into the existing M object. So insert entry. And before we implement insert entry, we can take a look back into our actual insert function. So here we can in fact use insert entry on our entry, and we then will also need to increase the counter. So M size plus plus. Oh, and that reminds me, we forgot something to save size. So it's actually good that we have this pre-created. Size is equals M size, but only if M exists. So we cache the so we copy the value here. The rest will be subject to change. And of course, our insert function here will need to some extent be aware of what we want it to do here because of the insert mode, or we just define that the insert entry is like an insert multi, so it always inserts everything, and then we will have like additional checking to enforce these modes. And I think this would be the most elegant approach, as it keeps the insert entry, which we'll use often here, as simple as possible. So even if it might have some duplication, it is probably the more efficient approach to have this here. So first thing we need in our insert entry is to find out the index of the bucket into which we want to insert our element. So here we can either use a helper function or implement this directly. I think we will implement this directly here. So our pnext, we'll give it a different name. We'll give it we'll call it entry. Oh, and I should have wait. This should be of course entry here. That was a small mistake. Now it's fine. So we have entry, and what we want to do when we are devising a index is we start with the hash value, and then we use a end, or rather we could use a modulo that's more fail-safe with the m bucket count. So we get a value which is 0 up to bucket count minus 1, and this value basically then represents our location in the bucket list where we want this individual entry to go. So we have this, so then we can go m buckets at index. Right, and here let's think about it. We need this to be a we need this to be a pointer to a pointer. So this is equals reference, and this is asterisk asterisk. I mean, we could simplify it. We just make a reference like this. This gives us the same effect. So now if we modify pbucket, then we will automatically modify the memory that is in our array here, since this is kind of a pointer on a pointer, just implemented by a reference. Right, so our p entry, next gets the value of pbucket, and our pbucket gets the value of our p entry. So we kind of, as mentioned, add to the top each time we add to the top of our bucket linked list, and the elements which are already in the list are moved one entry further down the list. So as you see, the insert function is quite simple. Oh, and we have forgot our release function, so we'll need to do that as well. And at this point we already have a working insertion, so very good. So let's quickly think about our release function. Yeah, so let's see, these are always pointers, so we will need to go through all the buckets and all the entries as we did here. The idea of the release function is, of course, it will also be used to clean up. So in the first case here, we did not clean up. That might be something that might need some improvement. So we should here again do it by reference, so that once we modify entry to be null, then this will contain only zeros. Otherwise, if we do release and then try to iterate for everything, then we would delete the elements, and we of course do not want that. So here we have more or less the same loop. We have next, we have right, we don't need this will be replaced with just deleting elements, so delete p entry, and then we go to the next. So this cleans up if there was anything to clean up. We could, since we know that this is cleaned up, kind of here add a fake optimization. Because like bucket count is not null, but bucket count is only relevant for the loop. So if we set it to null, to 0, then we forcefully always skip this operation. And this gives us the some advantage. So we don't need to check things which things which are already empty. And the content for our release, the rest of it we can just we should also check if m exists. Obviously we don't need this part, we just need 3 and m0. So we just 3m, and of course if m, or rather if not m, then return, because there is nothing to do. It's actually more pretty, so let's do it here the same way. Functionally it's equivalent. It might even compile to the very same code, but it just looks better to do it this way. So we have our release, which will delete everything if there is anything to delete. We have our create, we have entry. So now we would be already ready to test, insert something into our map. So actually we already have a test case, but just add a few more. 1, 2, 3. And let's run it and hope it doesn't crash. Also, one thing to say is, oh, it doesn't compile, so we have a mistake. Alright. That was a small copy and paste fail. Actually, we could kind of replace entry here with head, because it kind of will be using head. So let's just do this. Head. Right. Run. Right. So one issue we have is, in addition to it, of course m does not exist, so we need to check if m exists, take something else. We take 1. Right, in theory we could maybe do it this way. So if m exists, then we double the size. If it doesn't exist, we just first start with 1. But we also could have a hard-coded value that we always want to start with. For example, 16 entries. This would be a small optimization. We could also pass this as an argument to the constructor to pre-create something. So there are many ways we can optimize, which we'll explore later. Let's run it again and hope we have not forgot any other important safety check. Right, so this seems to work. As mentioned, there will be an issue with inspecting the map, since if we go to M, we only have buckets, and buckets does not know how many entries it has, so we could inspect maybe the first entry, but this would not really help us. So the next thing which would be good to have would be some option to print the content of our map, but this of course gives us a problem, since we don't since we operate with different types, we cannot easily print them. So we will create a print function, but one that is contingent on providing us the right function pointers to implement a print key and a print value. So void dump table. It should be called either dump map or just dump data. Dump table. Let's stick with dump table. Alright, so we want a we want everything to printf, so it doesn't need a return value. Void address print key, which takes const k reference key and a print value, which is almost the same, just takes v and value. Right, so we have our table, and we will want to go through the whole table. So we will want to iterate this time in a non-destructive way, which is quite easy. So first of all, printf. First of all, we print some header for size t. Right, size t, I is equal 0, I is less than m, bucket count. Right, we need to handle the case if there is no m. So if, oops, exclamation mark m, return and f empty. Right, so now we know there is an m, and we can continue with a good conscience. F bucket double point space, and that's it. No, let's give it percent there. Let's write down which bucket it is. It will be just counting 0 upwards, but it's always good to have the value. If you have a very large printout, then you don't need to count from the top. That is a small improvement. Right. Let's copy some code, because that's so convenient. Just need to ensure the code will not break anything. So we take the bucket from the top, we check whether it's null. We don't need this next entry here, because we don't mess with it. And then here we just make entry being the next entry for the next iteration. So here now we will have print key. I'm thinking whether we want a tab. Probably we want f backslash t. That might be too much. Let's just go with 2 spaces. So we have an indent. So we write the bucket starting at the line begin. We have an indentation of 2. Then we print the key, which is the key. Then we print a double point space. Then we print a value. Print value. Oops. Print value. Per entry value. And what we could do, we could print the hash. I think that would be nice. So we actually we can reuse this printer for that. We don't need a separate. So space brackets percent null x null x percent null 8x capital X. So we want to print it in hex format, and then of course we need to provide it. So entry hash. Right. This will be helpful to debug the hashing function, if it is working correctly, if it's providing a nice well spaced hash value, or if it is somewhat degenerate and, for example, always providing 0 or always switching between 2 values or something that would make the performance of our hash table be very inefficient, very non-satisfactory. Right, so we print this and then we are basically done. We could print something that there are no more entries, and that's it. So here now let's print our table, dump table. Right, we need our functions. So we will use lambda functions int key, right, semicolon. I think that's right. I think I didn't forget anything. And this thing will be our value %s punct c string. We could of course put such things into the template here, like a web printer object thingy. But I think since we already usually will do this, use this only for debugging, then it is fine to have the user to provide the functions here the way we did it now. So debug implementations don't need to be super user friendly. So we see here two bucket. Oh, I forgot some new lines. Let's see here. We want a new line, of course. After we printed everything, we want a new line. It was a quick fix. Right. So we have a table dump. Bucket 0 contains 2. Bucket 1 contains 3. And we have, since we always doubled, so we have bucket 2 and 3. One is empty. The other one contains 1. As you see, it appears to be completely unordered. That's also why for example, hash tables are in a still now called unordered map. Or maybe it was called unsorted map. I always confuse those two. For example, in C# you have dictionaries, and you can have unsorted dictionaries or dictionaries, and then the dictionary which is not unsorted will provide you a sorting, while the unsorted one will really behave like a hash table, and it will only be apparent to itself in which actual order the things are stored. So it's kind of called unordered or unsorted, but of course there always, as with computers, is some internal order to it. It just is not something that a human would recognize as order. That's why it's called this way. Right. So we have this. So what we could do now is implement our get function, which would kind of be already a very good milestone, because then we would have the basic functionality already working. It would not yet support the mode. Let's write this here as to the mode, and then we of course would want to have a bool remove key. Although we could have also remove key and value, which would be relevant if we want to specify a certain value if we have multiple values under the same key. So we will have a second remove that also takes a value, and then removes it. It of course returns false on failure. We don't need a find or something like we had in our list the last time, since a kind of get is automatically a sort of find. But we could have a v get value from key, which is different in as far as that it returns an empty implementation, so a new object, a copy of an empty value, if it doesn't find a value. And what also is quite nice to have is to use the square bracket operator. So it returns if vs v is the reference symbol, dereference operator square bracket key, of which we would want to actually have two instances. If we end const to do, this will also be to do's, but they're quite simple. They just use this one, and if this returns null, they will just throw an exception. The const might be an issue. The const might be an issue because this is not const, so we will either need to cast our this object or we'll define this as const. And since it does not change anything, we can, and then I will remove it here just for safekeeping. But this also means that we need to implement at least some of those things. So let's go with the operators since they are kind of simple. So right, so value asterisk values get pointer from key, right? And if then we throw an exception, else no, we don't need an else dereference, and we throw an exception. For now we just throw a string as an exception, but we can later create an own exception class invalid key. Wait, no, that's not what we want. Actually, we would want this to add elements if they don't find it. Then we should create a new empty element, add it, and then return a reference on it. And the const case the const case should not add elements because it's const. So one approach I think that Qt takes is that they just don't allow you a const operator, a const square bracket operator. If you want to use const, then you need to use get value, which is always const because it can return without crashing a just an object on the as a return argument. It does not. It is not contingent on there being an element to return. So in this case, if this happens, let's think how we fix that. Because here, for example, we kind of would need to look up again, which would not be what we want. So we actually need a helper function that will return us the entry that we have inserted. So let's create here a function, another one, the asterisk. I will call it insert pointer, and we will just basically it will be just kind of this function. Let's go with this. Let's go with this approach. So we will kind of move the whole inner content to the insert ptr, because this is the never failing version, and as a return value we will return the element which we have entered. Oh, and it doesn't return v, it returns as entry, although we could make it return v, that's fine. Value reference, right, okay. So, and if this would fail, we could in theory return null. So if value is null, then value is insert ptr from key and an empty value. So we just use the default constructor, and then we always return. So this way our square bracket operator always succeeds. And now we just need to implement here again. So again, to do mode checks, and other than that, if exclamation mark, then return false, else return true, and here of course value because we have it. Right. So the only thing that still is missing is our get pointer, and this is also quite easy. So first of all, if no m, then return null, obviously, because there is nothing to do. And else, we need the index. That we have a helper function. Is we had a helper function here, so we can copy this. No, we cannot. We need to first we need the hash. So we had this here. Right. So long hash is equals hash of key, capital H. So here we use just the hash we calculated with this, then we get the bucket. Right. And now we will need to go through the whole bucket, and which already, for example, implemented here. No. We have it in our dump as an example of a non-destructive bucket walking. So we copy this. So we have our bucket. This does not need to be by pointer because we do not intend to modify anything. Right, we could kind of start with just calling it entry. Right, and entry next. And if we kind of arrive at end without finding anything, then we return null again. But here internally we'll check if entry key is equals key. Then we will return entry a value reference on it. That is right. So of course, what we are missing now is an option to iterate through, for example, all of the values with the same key, but these are like advanced functions, so this will be for later. For now, we'll just do it like this, and since the other functions are really simple as well, I think it is fair for us to just at least implement this one. So here, of course, we said if we don't have anything, then we return an empty element, and of course we don't return the reference, but naturally we want it this way. We want to dereference that so that we make a copy. So here we will be making a copy that will be a bit more computation intensive than here, where we are kind of just returning a pointer. We just have kind of the asterisk here because we want to return by reference, which kind of is just a pointer return, but the compiler treats it slightly bit differently. So this is just a formality without a real effect, while here it will really make a copy to be created. So we have our get value, remove is a to do, insert and modes will be a to do as well. I think this will be all in all quite good performing with our helper function here. Yeah, we could have one improvement for the comment that if m then check modes, and if there is no m then there is nothing to do, because the first element always is to be successfully inserted. Do we actually have, yeah, and right here, as mentioned, we always return a value which is not null, so this is always successful for now, but in principle we could here inspect the return value and return failure. But I think it's more pedagogical if we do it just like this, so that we really indicate that, so that you don't think, okay, why would it be not true if it's always true. So just kind of we don't want to implement cases which in our current code base have no place. Right. And now let's add a test case. So we can disable the print auto map punct right, auto test m equals map from 2. Let's say we want 2. And then we just will inspect with the debugger whether test m is what it should be. Okay, so test m, as you see, it contains 2, so our hash table is working. Um, let's quickly now think of which other functionality would be nice to have. So since kind of we know that the functionality as provided by STL is a bit hard to use, so what would be really nice to have would be a cx list from keys to do. So a function which gives us a list of all the keys. There is a catch-22 here, namely that if the keys repeat, then we kind of will have them in our list multiple times, which might be something we don't want. So we'll need to think how to remedy that. One approach would be to just recheck the whole list, which would make it quite a slow operation, so we don't want that. Probably the easiest workaround would be to kind of do it, but only on a per bucket basis, so that we kind of make a temporary list. Then we check our each bucket. Within each bucket we remove duplicates, and then we might also have like a helper variable for that. We don't need to have like a temporary list which we then merge, but we could like have the main list which we return, and then a per bucket a list to look for duplicates, which probably is the most convenient approach. So here we will have all the keys, and of course then we will need to have an option to get a value if it's kind of further down in the hierarchy, so if it's not like the first value. So we could add here a how do we do that best? We would want a second parameter, basically an index. But then we also want to know when there was nothing more to return. So we would either want to have a get value, which would then take an index and a success or failure variable, or we would want it to actually return to us the pointer. I think we will go with adding such a function that does return the get value ptr and int x. Right. So this will be kind of just a wrapper to invoke get pointer, and we will just pass an index to it, so we can modify this with a default parameter equals null. The way this works is simply that here, so if key is key, then we just check if index minus minus equals 0, then we return, and if it wasn't 0, then we continue. Also, by the way, this should be a size t. So this way we will iterate through our keys. I'm thinking if we can maybe improve on that performance-wise, we could say if index is 0, then return, else in minus minus index. This kind of costs us 2 more lines, but we avoid an unnecessary operation, because in the most cases we will always be in this case. So okay, index 0, we want the first value, bam. But only in special cases we would want to ignore this key and look for the next value with the same key. Right, and we are running out of time, so I will upload this again to Moodle and the recording of the exercise. And of course, since it's exercises, we should think of some homework. As if I recall correctly, there was no homework last time, so here let's just add some homework this time. So 07/12/2023, implement the prepend function. Right, and we do the same with insert. Or actually, maybe let's just keep this as a to-do and write this here on at the top. Implement prepend function, implement insert function, and implement remove function. They all are very similar, and in principle prepend which I can be using so in principle prepend is just like an insert at 0, so that's like a one line one liner function. So these three functions will be the to do for the next lecture. The rest here we'll take a look later. So find will need some playing around, so we should do this during the lecture. You now have seen how to use function pointer, so we probably could do it, but let's not get ahead of ourselves. And of course for map, here we will think of some homework as well, if there is anything left. So this map is kind of it probably won't have much homework opportunity except maybe smaller things, since it's not super complicated, and it doesn't really have like repetitive functions that can be re-implemented. Yes, just in a slightly different way. But well, that's that. We will see each other next week, and have a nice weekend if that's already the weekend for you, or else we might see each other in the during the lecture later in the afternoon. Bye bye.